Okay, we're looking at problem 10 on the practice exam 2. Let's see, so we're supposed to find the area that is, let's see, inside that curve, but outside that curve. So the calculator is pretty much essential here. I've tried to badly copy the two graphs here. We can see the color difference here. The pink one is the sort of peanut-shaped one here. That's the first graph right there. The sort of more ovalish one is the blue one. That's the 2 plus sine theta graph. And so definitely graph these on your calculator for sure. So I have this set up in my calculator to graph from -4 to 4 on the x, -4 to 4 on the y, and start at 0, end at 2 pi, and the step, a pretty small step, so you can see more of it. So maybe about, actually I can say my step is set at about 0.02, so pretty tiny. It'll take a little bit longer to graph it, but you'll see more of the graph if you do that. So this will also help you to determine what region we're actually talking about here. It says the area that is inside this first curve. So the first curve is that peanut one, and then outside the other one. Okay? So inside the first curve, inside the sort of peanut-shaped curve, but outside the other one would be, let's see, where's that going to be? Inside this one, but outside the other one. I think what we're looking at then is this sort of region right here. And then it sort of continues over in this area here. Okay, so you can see that is definitely inside the peanut-shaped curve, and it's also outside of the oval-shaped one. Okay, so our goal then is to figure out where does this region start, for which value of theta does it begin, and for which value of theta does it end. So looking at this, I'm thinking symmetry we can use here. This region over here is exactly the same as the region over here. So really we just need to figure out where we're going to start this thing, what is the starting bound and what is the ending bound. Okay? So we can treat this in two ways. We can either say, all right, well, what's this region over here? Where are we going to start? Which angle is that? In other words, starting here, and where does it end down here? An alternative would be to start with a negative angle, in other words, sort of pointing straight down, and then sweeping theta up until we reach that intersection point there. So either one is fine. I think I'm going to go with the first one just so we don't have to deal with negative angles, though. So that would be basically we want to find that intersection point right there. What is that intersection point there? And what is that intersection point there? I think that one is pretty obvious. That is theta pointing straight down. That's 3 pi over 2. So really the next one we have to figure out is that over here. Okay? So to do that, we'll set these two functions equal to each other, okay? And we find the points of intersection, for which values of theta these intersect. So that's what I've done here. I set the two functions equal to each other. In order to solve this equation, we have to use a double angle identity for cosine. So we use the one that has sine in it. This is cosine 2 theta is equal to 1 minus 2 sine squared theta. We have to do that because the other trig function that we see over here is a sine. Okay, so now once we do that, we've got a quadratic with sine. So if we just rearrange everything, bring everything to the left side, we get this equation here, okay, quadratic. And then we can factor that equation like this: 2 sine theta minus 1 sine theta plus 1 equals 0. Solving the first one gives us sine theta is equal to 1/2. Solving the second one gives us sine theta equals -1. So the question is, where is the sine of theta equal to 1/2? Where does that happen? That happens at pi over 6 and 5 pi over 6 on the unit circle anyway. And then where does the sine of theta equal to -1? Well, that's 3 pi over 2, and that's the one that we said was maybe obvious that they're intersecting there. So we really only need to pick one of these. I'm thinking that we can start at the 5 pi over 6. That would be that one there. Remember, pi over 6 would be this one here. 5 pi over 6 is here, and then we'll sweep theta around until we reach theta equals 3 pi over 2. So those will give us our bounds. So for the area of this thing, we have to use the area formula for polar defined equations. So we get 1/2 integral, and then the bounds is what we were trying to figure out here. We're going to start this thing at 5 pi over 6. We're going to end it at 3 pi over 2. Okay, and then remember that it's the larger function minus the smaller one. The larger function here is at least in that region that we're concerned with here, the one that has a larger radius anyway, is the first one. So we'll have 2 plus cosine 2 theta, square that, and then minus the other one, the one that has a smaller radius on this interval that we're looking at here, 2 plus sine theta. We'll square that. So that's the integral that we have to find here. Let's go ahead and expand this and evaluate it. So we're going to have 1/2. In fact, actually, I'm just remembering that we were going to use symmetry on this thing, so that 1/2 is not even necessary. We're going to double that. So I'm just going to get rid of the 1/2. So get rid of the 1/2. That will give us the total area enclosed of the region we're actually looking at. Double that will give us the other one. Okay, so expanding all of this stuff, we're going to get 5 pi over 6 to 3 pi over 2. We'll get 4 plus 4 cosine 2 theta, and then plus cosine squared 2 theta, and then minus, if we expand that one, we'll get 4, and then we'll get minus 4 sine theta, the minus because of this here, so minus 4 sine theta, and then minus sine squared theta. Okay, and I'm trying to see if we've got any cancellation going on here. It looks like we do. Let's see. So it looks like at least the constants are going to cancel, the 4s will, and then the rest of it, yeah, we just have to leave it as it is. So let's see, that'll be integral from 5 pi over 6 to 3 pi over 2. Let's see, 4 cosine 2 theta plus cosine squared 2 theta. Actually, I'm gonna put the sines and the cosines together, the first power, so minus 4 sine theta, and then cosine squared 2 theta, and sine squared theta. Okay, so let's see. The first two, not bad. We don't have to do anything, any identities for that. So the antiderivative of 4 cosine 2 theta, that's going to be, well, let's just do cosine 2 theta. The antiderivative of that is sine 2 theta, and then we're going to have a 1/2 on there. So we'll get 2 sine 2 theta. And then the second one for antiderivative there will just be negative cosine, so we'll have a plus 4 cosine theta. The rest of this thing here, the cosine squared of 2 theta, I'll try to squeeze these in up here. For that first one, we have to write that as 1/2 plus 1/2 cosine 4 theta. Okay, that's the power reducing identity for cosine. And then for the second one, we're going to have to write that as, since it's minus, we'll have to say minus 1/2. That'll be minus, the identity is minus there, but we're going to have to change that because we've got the minus in front of here, so it'll have to be plus 1/2 cosine 2 theta. Okay? So fortunately, it looks like these 1/2 terms are going to cancel each other out. So really, that's the two that we have to find. Two antiderivatives we need to find there. Let's see. Yeah, in fact, actually, we could have saved ourselves a little bit of work here because that term there is the same as that one. But anyway, we'll just deal with that at the end. So anyway, the antiderivatives we actually do have to find here would be these two. Okay. The antiderivative of cosine 4 theta, that's going to be 1/4 sine 4 theta multiplied by the 1/2 that's already there. I'm going to get plus 1/8 sine 4 4 theta. And then this last one here, I'll have to multiply that by 1/2 as well, so I get a plus 1/4 sine 2 theta. Okay, and this is where, again, if I had noticed that, I would have combined this one with that one before doing the antiderivatives. But anyway, in fact, we can just go ahead and do that now. So let's just do this one more time, but I'm going to just simplify this a little bit so we don't have to plug in so much stuff. So if I combine our two sine 2 theta terms, there's a sine 2 theta term there, and there's another one there. Combine those 2 plus 1/4, that's going to be, what is that, 8/4, what is 9/4, so we're going to have 9/4 sine 2 theta plus 4 cosine theta and 1/8 sine 4 theta. Evaluating this between 5 pi over 6 and 3 pi over 2. Okay, so hopefully I'll have enough room to finish this. If I plug in 3 pi over 2 to this thing, 3 pi over 2 here, the 2's will cancel. I'm going to have the sine of 3 pi. Sine of 3 pi is going to be 0. Okay, so the first term is 0. Second term, when I plug 3 pi over 2 in there, the cosine of 3 pi over 2, that is also 0, so that term will also be 0. If I plug 3 pi over 2 into here, then the 2's are going to cancel. I'm going to have 2 times the 3, that's 6 pi. So the sine of 6 pi, that's also 0. So all of the terms are going to be 0 on the first one. If I plug in 5 pi over 6 now, remember now I'm subtracting, so I'm going to actually get negative of whatever I get when I plug 5 pi over 6 in here. So if I plug 5 pi over 6 into here, let's see, the 2's are going to cancel, so 5 pi over 3, so 9/4 times 5 pi over 3, the sine of 5 pi over 3. Sine of 5 pi over 3, what is that? Negative root 3 over 2. Negative root 3 over 2. Then when I plug 5 pi over 6 into the next one, the cosine of 5 pi over 6, it's going to be 4. Cosine of 5 pi over 6 is negative root 3 over 2 also. And finally, when I plug 5 pi over 6 into here, let's see, the 4 will become a 2, and that'll become a 3, so I'll get 10 pi over 3, is that right? Let's see, 20 over 6, yeah, 10 pi over 3. So the sine of 10 pi over 3, so plus 1/8. 10 pi over 3, let's see, that is coterminal. 10 pi over 3 minus 6 pi over 3 is 4 pi over 3. So we're looking for the sine of 4 pi over 3. The sine of 4 pi over 3 is negative root 3 over 2 as well. So we've got all these negative root 3 over 2 terms. Okay, and just want to make sure that we're approaching our correct answer on this thing. Seems to be. So let's see what happens when we put all this together. We're going to get, notice that all of those terms were negative, but we had that negative in front because of the fact that we were, fundamental theorem subtracting. So in fact, all the terms will become positive. So I will get 9 root 3 over 8. So 9 root 3 over 8 for the first one. I will get minus 2 root 3 for the second one, or actually plus 2 root 3 for the second one. And there I'll get root 3 over 16. So plus root 3 over 16. Now I'm just going to make sure that this does indeed add up to 51 over 16. Let's see, so we get 9 eighths plus 2 plus 1/16. Wrong screen. 9 eighths plus 2 plus 1/16 is 51 over 16, and perfect. So this is, put all this together, we get 51 root 3 over 16. A lot of work on this one.